Thank you for joining the Food Safety Educational Conference as part of the 2021 Virtual Southeast Regional Fruit and Vegetable Conference. I'm Laurel Dunn, Food Safety Extension Specialist with the University of Georgia, and I will be the moderator for this presentation. First, I'd like to thank Highland Ag Solutions for sponsoring the 2021 Food Safety Educational Conference. Let's watch this short video provided by Highland Ag Solutions.
Highland is virtualizing the business of agriculture. From soil to sale, we are uniting growers, packers, marketers, and their customers in ways never done before. In today's global marketplace, competition has never been fiercer. You need innovative tools to provide business and market transparency for the industry to remain sustainable for future generations.
Pesticide CEU and CCA credits are available for most presentations offered during the live Southeast Regional Conference. Check the Pesticide CEU guide for a list of approved presentations and participating states. The Pesticide CEU guide is located in the Event Resources tab under the Media player. The guide is also available at the Resources Center located on the main menu of the conference platform. Please note, pesticide credits will only be available for registered attendees and only during the live conference. Credits will not be available for on-demand viewing. There is a simple three-step process to receive pesticide CEU and CCA credits. First, go to the audience chat box located on the left side of your screen and type your first name, last name, and the states for which you are requesting credits. Again, go to the audience chat box located on the left side of your screen and type your first name, last name, and the states for which you are requesting credits. You'll need to do this for every presentation in order to receive those CEU credits. The second step is to sign out at the end of every presentation. To sign out, go to the audience chat box and type your first name, last name, and the states for which you are requesting credits. You will be reminded to sign out at the end of the presentation. The third step is to complete the pesticide CEU registration. You only have to complete this registration one time during the conference. This is not required with every presentation. To access the pesticide CEU registration web link, open the pesticide CEU guide on the Event Resources tab located under the Media player. The Pesticide CEU registration web link is located on the front cover of the guide. This presentation is pre-recorded to reduce technical difficulties. We will be answering your questions live at the end of this presentation. You can submit a question at any point during this presentation by typing your question in the questions box and pressing send. Don't forget to thank our 2021 conference sponsors and exhibitors by visiting the virtual trade show and featured products pavilion. And finally, don't forget to join us each morning for coffee chats and each evening for networking. Check the conference agenda for details. Now I'd like to take a moment to introduce Dr. Gary Hawkins. Dr. Hawkins works for the University of Georgia as the Water Resource Management Specialist in the Department of Crop and Soil Science. He's an agricultural engineer and graduated from Clemson University, Auburn University, and the University of Tennessee. He is responsible for extension programming in the areas of water quality, water quantity, and water resources. His current extension and research programs are related to water resource issues in the areas of soil and water conservation, water retention, water management in various crops, nutrient movement, well water protection and education, septic systems, water quality, water quantity, and small-scale irrigation. Today, Gary is going to present the talk, Well Health, Is Your Well Safe from Contamination? Thank you, Gary.
Thanks, Laurel. I appreciate y'all having me here today, and thanks for asking me to do this. So, like Laurel said, I'm Gary Hawkins. I'm the Water Resource Management Specialist here in the Crop and Soil Science Department at UGA. And Laurel asked me to go through what wells are, how we look at well water quality, well water quantity, a little bit, what a well system is, and then how do we test that water, and what are some of the tests we do. So we'll get started. So the first thing we need to look at is what is a well. A well, by definition, is a deep hole or shaft sunk into the ground to obtain water, oil, or gas. And so obviously today we'll be talking about mostly water. And these two pictures here, a lot of times I think when we think of a well, we think of that on the left, a bored well with the bucket there that we lower down, we bring water back up. But typical wells that we get drinking water out of, water for produce houses and production houses and other sources, is the well on the right. So we will drill a hole, various sizes. Home wells are typically 4 inches, 6 inches maybe. If it's a large production well for a packing house or for irrigation, they may be upwards of 24, 36 inches. So, but it's all the same. It's basically a shaft in the ground or a hole in the ground, multiple depths from 80 feet in some parts of the country down to hundreds and hundreds of feet. You see there, it can go through also multiple layers of rock and sand and into, you see there, the blue is the aquifer, and we'll talk a lot more about aquifers as we go through. So when we talk about aquifers, we have to look at two different kinds. You see there in the middle of the screen, unconfined aquifer in that kind of darkish blue, and then you see a confined aquifer there in the lighter blue. So you see 3 wells, that artesian well, the flowing artesian well, and then on the far right there, the water table well. I'll start with the water table well. That water table well is sort of like that bored well that we saw earlier, kind of has the same configuration there. That well is typically maybe in the 30 to 40 foot depth, generally 3 to 4 foot in diameter. And generally what you'll see is you'll have a pump in it. Sometimes you may have the bucket that you lower into it to get that water out. It's called a water table well because you see it's in that darker blue or that unconfined aquifer set. And so you also see there in the well that light blue, that is the water table. And these water table wells actually follow the water table. So if it's a real rainy season or it's the rainy season, the water in that well may go up. If it's a dry time, like when we're in drought, that water will go down potentially. So that water elevation in the well will follow the water table pretty close. The other side, you see the other 2 wells there, the artesian well and the flowing artesian well. You see they're stuck down, if you want to call it that, down in that lighter blue or confined aquifer area. The artesian well is a little bit higher than the middle flowing artesian well. And you also see that dotted line there, the potentiometric surface. With that confined aquifer, the water pressure in that aquifer system itself wants to push the water up to that potentiometric surface or that dotted line. So in that artesian well, you notice that the blue is at ground surface or right at that potentiometric surface. And in an artesian well, the water will come up in the well from that deeper confined aquifer, but it won't overtop the well, if you want to call it that. The middle well there, the flowing artesian well, you see the mouth of that well is right at or right below that dotted line or potentiometric surface, which means the water wants to be at that dotted line level. And so since the mouth of that well is below that dotted line or potentiometric surface, water will actually flow out without a pump or anything. So when you hear those words, artesian well, that means the water rises in it by itself, or flowing artesian well means the water flows out of it without pumps or anything. When we then look at a well system, the image there on the left is a schematic of a typical household well, but it could be for packing houses or other operations. I'll call it the center of the image there. You see the well. It's got the pump there in the bottom with the motor and the pump itself. You see the well screen, and I'll show you a little bit more about that in a minute or two. But you have the well itself. And then you see there the pressure tank on the left. For a typical household, that would be our well or our pressure tank, 30 to 60, maybe 120 gallons or so. What happens is as the water in that tank goes down, the pressure in that tank goes down, and it causes that pressure switch to engage electricity, which then engages the pump. The pump then, in essence, fills up that pressure tank. Once the pressure reaches typically 50 or 60 pounds of pressure, the pressure switch cuts the system off and cuts the pump off. So in a house situation, we actually more than likely are using water out of that pressure tank. So what that does is it causes or it relieves that pump from cycling off and on every time we turn the spigot off and on. And I'll show you some of the troubleshootings about that later and why that could happen. But the pressure tank's there to really absorb a lot of that energy and cause that the house pressure to have a lot or have the same pressure. Same thing occurs in a larger operation. If you've got a pack-in house, if you've got other resources and other needs, your pressure tank may be a lot larger, but it works the same way. It has a constant pressure on it so that your pump's not cycling off and on. The right-hand picture then is a schematic or a real mock-up of a well. We took this up when we were at Virginia Tech a couple of years ago, and you can see the white is the casing that would go down into the aquifer. The bottom shiny silver part there is the pump and the motor itself. That black football-looking thing is a stabilizer. So you put those down in the well to keep the pipe and the wires centered in the well itself so they don't rub against the side of the well, and then on up to the ground surface. And we'll talk about caps and the ground surface here in a couple slides. So when we talk about those wells, I mentioned well screens in deep wells and shallow wells. This is a schematic or a drawing of a deep well. This would be, at least here in Georgia, in the coastal plain area, where we have that impermeable layer there in the middle, where we would typically go down into the Florida aquifer system. So down into that deep confined aquifer. As you see, we have that grout seal in that impermeable layer. What that does is as they drill down through, they'll set that grout seal layer to keep the water from the confined aquifer from intermixing with that unconfined aquifer there at the top. You'll see the filter screen, the green dashes there. What that is it keeps the sand and all the larger particles from getting into the well itself, and therefore messing up your pump as the pump pumps the water out. On the top of that, you see, in this case, an outhouse or any other contaminant source with the red triangles. And you notice that water, that superficial aquifer water, or unconfined aquifer water, does not intermix with the lower water. So in a deep well situation, this is what we're looking at. And then a shallow well situation, like that first picture I showed, and we'll see it on the next slide as well. With those bored wells, typically they are dug down to the impermeable layer. So again, this may be 30, 40 feet deep. But the thing is, they are pulling in the superficial aquifer water. And again, with our outhouse or our contaminant source, whatever that may be, that superficial aquifer or those shallow wells, if there's any contaminants in that aquifer, they potentially and typically will get into the well. So testing your groundwater in these situations is a lot more imperative than maybe even the deep well. But we also need to test the deep well as we go along, and we'll talk about that here in the next couple slides. So again, when we're looking at wells, one of the things we need to do is maintain that well, and we need to protect it. And again, we will look at, over the next probably 10, 15 slides, how do we protect that well, and what are those things we need to do to maintain our wells. Maintenance, the biggest thing with maintenance is just making sure nothing gets down into that well casing itself or that PVC pipe. Like I mentioned, it can be anywhere from 4 inches to 24 inches, depending on the size and the amount of water you need. But when we start talking about maintenance, what we really need to look at is this well cap or this well seal. And the well cap needs to really be tight, and the well seal as well needs to be tightly secured. And the purpose of that is to keep any surface water out of the groundwater well. Not knowing what's on the surface and getting surface water down into your well is not a very good thing. You want to keep any insects or any other animals out of that well. When they get in, they can defecate, they can die, they can do anything else. And then that's where some of our bacteria and a lot of our bacteria actually gets into our well. So keeping those vermin, those insects and other creatures out of our well is the purpose of the well seal or well cap, depending on which one you have. Fertilizers, we definitely don't want nutrients down into our well, because that well water we pull back out goes straight to our sinks and then our glasses and our drinks and whatnot. So we want to keep the fertilizers and especially the herbicides out. And then we definitely want to keep our pets out of it, because we don't want our pets falling down in these wells. So having a good well seal and a good well cap on those wells is almost imperative. So when we start looking at the well seal, if you have a company or when you have a company come out to drill your well, this is going to be what a typical well with a well seal is going to look like. So you have the well seal you see there, that black cylinder or black ring there. You'll have an installer tag. What that'll have on is the depth of the well. It'll have who put it in and the date. And that's important because if you ever need to go back for chlorination or any other reason, knowing the depth of that well, knowing where the static water level is, all that information can help whomever figure out how to chlorinate that well and some other aspects to it. You see the sealed electrical line port coming out. That's the electricity that goes down to the pump in the well. So that's a good tight seal. Doesn't let any of those herbicides, pesticides, fertilizers, insects into that well itself. You see the vent, there can be pressure built up in the well itself for multiple different reasons, but that well vent allows a little bit of air exchange and really pressure exchange within that well itself. You notice we have a hose bib here, but it's called a threadless sample tap. We definitely don't want to hook up a garden hose or whatever to the well itself, but we may want to take a water sample. And when we test our wells for water, we want to a lot of times get a well sample, and having this threadless sample tap right here allows us to get that sample without having somebody mistakenly hook up a garden hose to it and use it as the watering source. Some of the other things we need to do is we need to have good well caps. And so you look at these two pictures, a lot of times in regulations, depending on which state you're in, requires or you should at least have the well cap or the well seal 8 to 12 inches above ground surface. And that comes back to not letting surface water into your well. So the picture on the left is down in a well itself. It's down below grade level. You see the white pipe coming up so they can actually access that water. Typically, we don't want a well cap like that, or a well seal or a well cap below grade level. The one on the right is well above grade level to keep any kind of water out. So which one's good and which one's bad? Obviously, the one on the left is bad. We don't want that situation to try to keep as much water out of our well as possible from the surface. The one on the right being 12 inches or so above ground surface will protect that well a lot better. Some of the other things we need to then think about with maintenance is how do we maintain the area around the well? So the one on the left there you see is a home well. They've got a good concrete pad. They keep the grass mowed around it. So that's a good way to maintain anything around that well. There shouldn't be any water or shouldn't be a good way for water to get down in that well from the surface. Same thing on the right. From an agricultural side, that's a good setup. They got the concrete pad there. It's maintained around it. There shouldn't be any way for water to get down into the well from the surface in that situation either. Some of the other things when we start looking at maintenance is we want to make sure we keep any chemicals, gasoline, fertilizer, any of those things that potentially could get down in the well and contaminate that well at least 50 feet away from the well. In this left-hand picture, you see the potential fertilizer tank back there, the green one. If that one happens to have a leak, the pad looks like it's a little bit higher than grade level, but if there's a lot of fertilizer in that tank, it could leak over onto the pad. And really depending on how well that seal is around the well itself, some of that fertilizer could get in. So one, keeping that fertilizer away, or if this is a fertigation system, maybe even having a secondary containment around that fertilizer. So if there is a spill, then it's contained and doesn't get near the well itself. On the right-hand side, you see the 5-gallon buckets back there. That could be oil or chemicals or something else. We definitely don't want that around our wellhead because, again, if there's a leak, if there's a heavy rain, if there's any kind of way that could get down into the well, we definitely don't want those materials down into our well itself. I've mentioned a couple different times we want to try to keep surface water out of our well, and one way to do that is to make a little, if you want to call it, cap over on the concrete pad. So if you see on the left one here, it's kind of hard to see, but around the well itself, the concrete is sloped away from the well, and what that does is actually keeps the water, surface water, away from that well itself in case there is a slight gap in between there. And it keeps that water going away from the well. Same thing on the right, you see the pad is not necessarily sloped away from the well, but it's a couple inches above grade level. So if there is, for some reason, a lot of water on that ground, it's not going to get near that well itself. So I mentioned earlier about some different issues with our wells. Some of the typical warning signs that we have a problem with our well, the pump's constantly cycling on and off, and I'll show you some of the troubleshooting, but that could be related to your pressure tank. Is there a drop in water pressure? That can have a lot of different possible solutions or issues with it. Remember we talked about on that first or second slide, I guess it was, that if the water level drops in a drought situation, that can cause the water pressure to drop. And those pumps that you put in there, the submersible pumps, are designed to pump so much water at what they call so much hydraulic head. And if that hydraulic head changes due to water going up or down in that well casing or the water table going up and down, the water pressure that you get out of that pump can change. Does the water have a strange odor or taste? And we'll talk about that on the next slide itself as well. Are there particles in the water? And is there a damaged casing? So all these things are warning signs that our well system is having problems. Here at the Extension Service at UGA, and I know across the Southeast and really across the U.S., these are a lot of the questions that our county extension agents can help answer. Dr. Dunn, myself, can answer some of these questions as well as what's going on with these well systems. So I mentioned some of the problems. If we look at, and you're having sand or sediment in your well, is the well properly constructed? Has it been, since the well was put in, are you having sand and a little bit of silt and sediment coming out the next couple days? That could just be the well cleaning itself out. That may not be that big of a deal. But if you have sand or sediment or something in your well water months or years after the well's been installed, it could be a hole in the screen. A lot of times if we have a real dry period and then we get a lot of rain thereafter, you may see some sediment due to the hydraulic change of that water pressure in the aquifer itself, pushing some of those fine particles through with the extra hydraulic head behind it. I'll jump down then to the bottom to changing that color, taste, or odor in your water. There could be some contamination in your water. That could be bacteria. That could be some other chemicals or whatnot. And this is then a good time to check your water, send it to the lab, and have it analyzed. And then the last one there, well damage, a cracked casing, loose missing cap, or exposed wires. Some of the possible causes, and we hear this a lot. Somebody backs into a well, especially if it's a 4 or 6 inch well, kind of out by itself. If somebody backs into it, it's going to change the direction of that pipe a little bit, and it could cause the casing to crack, which isn't going to let water into the well itself, or other issues that could be possible. So if a lot of times, I know when we go out or I work with the agents, I'll ask them these questions. How long has it been there? When did the taste, odor, color change? And has anybody backed into the well, or can anybody back into the well, as we start looking at possibilities of why the water quality has changed? So I want to talk a little bit then about well water testing and analysis, and what we do and how we do with that. So when we test our well water, some of the reasons we want to test it is some chemicals can't be seen. So think of some of the things you put in your water, and I'll just use Clorox, for instance. So if we using Clorox at our house to clean with, once we pour that Clorox in the water, other than the smell, we can't see that. So there's some chemicals that get into our water that we just can't see. Pathogens like bacteria that get into our well water, we definitely can't see them. A lot of times, really nutrients, we can't see nutrients and nitrates, phosphates, those things that get into our water, we can't see them. And then sometimes when the water looks bad, it can only be sediment in the water. I mean, there may be nothing else in there except a little bit of sediment. And so sending the water samples in for a test can tell us if there's chemicals, pathogens, nutrients, or if it's just sediment. And if it's any of these things, we can set up filter systems, but the first thing we need to know is what's in that water. And we'll talk about some of the water tests here on the next slide. So when we start looking at water testing, and I'll just use, I know this is a Southeast Regional conference, but I'll just use UGA's water test. And so when we start testing water quality at our Ag and Environmental Sciences or Services lab here in Athens, when we recommend water tests for homeowners or for packing houses, the three we're probably most likely going to tell you to look at and work with is going to be the W1 basic water test, the W2 expanded water test, and the W35 total coliform test. The basic water test really just tests your pH, your hardness, and some of those minerals that might be in the water. Here at UGA, they require a 125 milliliter sample bottle, and the cost of that is $20 at the lab. But then if you go through the county extension office with shipping fees and some other things like that, they will maybe charge you a couple extra dollars to help cover the cost of shipping. So again, the basic water test is just to kind of get a feel of what's in that water, and how we do it. And you can get the bottles from, at least here in Georgia, from UGA extension offices. The W2 then is the expanded water test. You see there is the basic W1 test, but also includes some of the anions, the soluble salts, and alkalinity. A lot of times we'll do this in case you're having problems with some of the minerals in your water. We may suggest a W2 to get a little bit more information about that water coming into the house or into the packing house or wherever you're using that water. This one requires a little bit more water because you're doing a little bit more tests, and the cost on it, you see there, is a little bit more than the W1. The third one then is a W35, or the total coliform E. coli test. This one is required. It requires a special bottle, and I don't have a picture of the bottle, but when you get it from the extension office, it has a white powder in it. The biggest thing is don't pour that white powder out. Don't rinse it out, because it's in there for a purpose to help preserve that sample prior to getting it to the lab. And we use these this W35 test for drinking water, irrigation water, the GAP program. And there's certain forms that are needed to be filled out. So make sure you go, at least here in Georgia, go to the website and make sure you get the right forms. Now, if you're also looking at your FSMA produce safety rules stuff, and you're having to meet those requirements, this same W35 test meets that requirement. The cost of it, you see there's $36 typically, then $10 extra, and they'll provide you the overnight shipping package. And if you do a total coliform or W35 test, due to the way they have to run them, those are only accepted Monday through Thursday, and that gives them Friday to catch up on Thursday's samples that come in. So just kind of go through a few reminders. If you're looking at your wells and you're interested in what the well regulations are, those are going to be state specific. Generally, they're going to be the same, but Alabama may be different from Georgia, just slightly different from Florida, just slightly. So make sure you know what the real well regulations are in your state. When we protect the well water, we definitely need to have a good well seal or well cap on there. And again, you see these are both at least 8 to 12 inches above ground surface or surface level. That again is to help keep any of that surface water out of our well to protect that well itself. We want to keep the area around the wells well maintained. You see this one has a nice cap, a nice pad around it, and it's maintained around it so that if anybody's driving next to it, they'll see it, or other reasons, but it's maintained around that so that this is well seen. One of the things, we need to have a good pad around the system. So on the left there, we saw this picture earlier. It's got a nice pad around it, concrete pad around it. It has a little bit of slope away from the well itself to keep any surface water from going into the well. It keeps that water out. On the right-hand side, then, are two kind of bad, if you want to call it that, well heads. First, we definitely don't want to have pallets as our well cap. Now, this could have been in production, and overnight they left it there. But again, we've seen some that this is the well cap for operating wells, and we definitely don't want that. The one on the far right then, it's got a nice pad around it. It looks like 3 or 4 inches of concrete around it, but you notice that it's caved in under it. So having a good pad in this case is not the best in the world, because water can still get around that casing. So, you know, this definitely would need to be fixed. We definitely don't want to store our chemicals near the well, so we want to keep those at least 50 foot away. The chemicals, the gasoline, any other organics. Again, we don't want any of that material getting near the well head itself that potentially could then get into the well. And then the testing part. Well water testing should be done for packing houses to make sure you've got good clean water coming into those packing houses. In homes, we suggest you do an annual water test, and generally we suggest that in the spring. And the reason for the spring is that's when we get a lot of rainfall in the springtime. We get a lot of that hydraulic pressure in the aquifer, like I talked about. And if we get anything coming through, it's more than likely going to be in the spring. And if you do it the same time every year, it's like going to the doctor. We want to kind of get that annual checkup, and this is a way to get our annual checkup for our well itself. And then what we do here at UGA, at least, is suggest that the first year when you initially take a sample, do that W2, that expanded test, to get all the components in it as kind of an initial amount of what's in that well. Then the next 2 years, you might want to do a W1. It's the basic well water test. It gives you, as the W2 has the W1 as a part of it, it still gives you the pH and those minerals. And then that fourth year, go back to a W2 to catch up those soluble salts and those other things, including W2 that's not in W1. And then that bacterial test, that W35, we want to do that annually. And the reason for doing these, again, is we typically go to the doctor every year to get our physical, our annual checkup. This is just a way to get our well water an annual checkup. And so with that, I'll finish up, and Dr. Nunn, I'll turn it back over to you. But again, thanks for having me here. And again, I'm Gary Hawkins. I'm the Water Resource Management Specialist here at the University of Georgia. So Dr. Dunn, I'll turn it back over to you.